Hello. Today we are solving a problem on the application of friction force in concrete situations, and let's look at the first case. The physics lab students are planning an experiment to determine the coefficient of static friction between a pumpkin lantern weighing 1.8 kilograms and the tabletop on which it stands. The basic procedure is to slowly pour sand into a bucket, which is suspended by appropriate threads until the pumpkin begins to slide on a given surface. The bucket of sand was then weighed on a scale and its weight was found to be 11 newtons. Determine from this data the coefficient of static friction of the lantern against the tabletop. So the figure is shown, and our task now is to see how we can carry out this procedure of estimating the coefficient of friction. So let's fix it as an unknown value. And record the data that was in the problem. The mass of the pumpkin lantern itself is 1.8 tenths of a kilogram. And the weight of the sand bucket, once it's all moving, is 11 newtons. What can we do in this task in terms of solutions? When we encounter the movement of several bodies, which, let's say, are interconnected, we must understand that we need to describe the movement of each object because each of them experiences the action of certain forces, and then we can solve the resulting system of equations using certain laws. To do this, now in the figure, let's show what forces will act on each of these bodies at the moment when the movement of this lantern began. We will consider a situation when this transition has not yet occurred, but it is about to happen from rest to sliding, and we can say that the forces at this point in time are still compensated. That is, the forces acting on each object add up to zero. Let's arrange the forces acting on the bucket. In this case, here we will work directly with the weight, which we have measured. That is, it turned out to be equal to 11 Newton, and of course the tension of the thread, which prevents the bucket from falling, will act. As far as this lantern is concerned, in this case, is being propelled forward. The same tension because we are talking about the same thread. Naturally, in this case, the weight of this lamp acts. Let's designate it as weight number 1. The reaction force of the support from the surface will act and will act. The friction force of rest. So in this case, we're looking at the extreme transition from rest to sliding. Let us then describe the conditions of equilibrium for each body in sequence. For a bucket with sand, we can say that its weight in this case is compensated by the force of tension of the thread. As for this lantern, we have to describe two types of equations. That is, we have motion along the x-axis, and so the forces acting along it, and there are also forces acting along the y-axis, the coordinate axis. In this case, we can take arbitrary, classical, we can consider this coordinate plane. And on the x-axis, we see that the tension of the thread is compensated by static friction. The force of the support reaction vertically is compensated by the weight of the object, of this object. Now our task is to solve the resulting system of equations. The first part is clear here. The weight of this bucket has been measured, so the force of tension will also be known. Let me remind you that the force of static friction depends directly on the given coefficient of friction, which we are now determining, and the force of interaction between the body and the surface. In this case, it is the force of reaction of the support. By the second equation from this system, we see that the force of the support reaction is determined by the force of gravity acting on this pumpkin. Then let's put all of that into our equation. We get that the tension of the thread is equal to the product of the coefficient of friction by the gravity of this lantern. Well, the force of the thread tension is determined by the weight of the sand bucket, so let's make the same substitution here. But the result is this expression from which we can already, to determine the value of this coefficient of friction, it will be the ratio of the weight of the bucket of sand to the weight of the lantern. Lantern The weight of the bucket with sand is known, and the weight of the lantern we can determine as the product of the mass of this lantern by the acceleration of free fall. It remains to put numerical values. So the weight of the bucket is 11 newtons. The mass of the lantern is 1.80 kilograms and the acceleration of free fall is 9.81 hundredths of a meter per second squared. Kilogram per meter per second squared is we have a newton, on top is also a newton. Of course these units are reduced and we get a dimensionless quantity. The answer is roughly 0.62 hundredths, which is quite a normal value for the coefficient of static friction. Let me remind you that its value can fluctuate from 0 to 1 if we take the lowest and the upper boundary, so you can estimate the correctness of the solution to your problem by the answer. So, this is the first problem solved. Goodbye. See you in our next lessons.